Hello everybody. This is our lesson on average rate of change. It goes along with section 12.3 in Math Excel. So our goal today is to find the average rate of change of a function over an interval. And then that's going to lead into finding the instantaneous rate of change of a function at a point. So what I want you to do first for our introduction is to pause this video, go to YouTube, and click on that link and watch the video, What Are Speed and Velocity? It's from the Physics in Motion series. And then come back to this video. Okay, hopefully you've watched Physics in Motion and you looked a little bit at speed and velocity. This is a graph from that video, and where on this graph is our car moving the fastest? Think about when you're moving fast. You're covering a lot of position, but in a little bit of time. So if I look at this graph, where on it do we cover a lot of position in a little time? In these steep intervals. Position is changing a lot, time is changing a little. If I put a point there and do my best to draw a straight line tangent to that curve, you'll notice that that slope is rather steep. And where is the car moving the slowest? Well, think about where you move the slowest on the road. It's when a lot of time passes, but you don't go very far, like on the highway when we're trying to get home after school. Not much distance is gone through, but you sit there forever. If I draw a line tangent to the curve at these points, my slope is rather low. There's low change in distance over time. Now we're going to look at an equation that describes a relationship between distance and time. And one of the most common ones we see in physics is the relationship that describes the height of a projectile. And that relationship is typically y equals 1/2 acceleration due to gravity x squared plus initial velocity, that's velocity at time 0, times x, plus initial height, that's height at time 0. The negative 32 is negative 32 feet per second. That's acceleration due to gravity, and it's negative because you're pulling things toward Earth and not away from Earth. In my example, I was going to use S and T, but I decided later on to switch everything to Y and X just to keep it consistent with the mathematics we're going to be doing later. But you see it a lot in physics with different variables, S for distance, T for time. And now we want to think of the concept of average velocity. When we think of average velocity, when you're driving along somewhere, how do you calculate your velocity? You take your change in distance divided by the change in time. So if you go 100 miles and it takes you 2 hours, 100 miles every 2 hours, your average velocity was 50 miles an hour. Does that mean you went consistently 50 miles an hour the whole time? No, of course not. You hit stop signs, you go faster on the highway, you go slower on slower roads. But your average velocity is change in distance over change in time. And if my distance variable is y, y2 minus y1 over x2 minus x1, when my y is distance and my x is time. Now, let's use this equation. For my, in this example, tennis ball. A tennis ball is dropped from 100 feet. We want to find its average velocity from 1 second to 2 seconds. So at 1 second, it's at this height. We're going to calculate that. At 2 seconds, it's this height. I want to find its average velocity, which is simply the slope of a straight line that goes through those 2 points. So I want to find my height, which is my y value, at 1 second and at 2 seconds. So at 1 second, I have negative 16, 1 squared plus 100, which is 84 feet. And at 2 seconds, I've gone negative 16 times 4, which is 64. 100 minus 64 is 36 feet. So my average velocity is my change in distance minus my change in time, which is 48 feet per second, and it's negative because of the 1 minus 2 in the denominator, or think of it as you're falling toward Earth. So that's my average velocity at the interval. Now, does that mean my tennis ball is going negative 48 feet per second at every instantaneous minute? No, it goes faster as it's dropping closer to Earth. However, that's the average change. All right, let's look at another example. A particle moving along a horizontal surface. So we have a particle, we're rolling it or pushing it, or somehow it's moving across a horizontal surface, and it's going from point 1 to point 2, and we're measuring how many feet it goes each second. But realize it might not be going at a constant rate. It might start out really fast and then slow down over time until it gets to that second point. We have these measurements, but we want to calculate its average velocity at time 5. But I've only taken measurements at 1, 2, 4, 6, and 9. So how do we find average velocity? Well, change in distance divided by change in time. So 20 minus 13 over 6 minus 4, and I get 7/2, or 3.5 feet per second. That's our average change of rate, our average rate of change. Now what I want you to do is I want you to pause the video, and I want you to complete the Desmos activity on our Desmos class, average rate of change. And remember our code to our Desmos class, I forget what the code is, but it's posted on Schoology. And I want you to do all the slides, but when you get to the slides indicated, 4, 7, 10, and 12, I want you to write your work and write your answers to the questions here in your notes. And then when we come back, we'll talk about it in class. But when you get to that point, do your calculations here on paper. You can work with others in your group on this activity. Go through the activity together. And then when you're done, please turn back on this video. Okay, we have looked at average rate of change, and now I want to take a look at an example. And the purpose of this example is to show you 4 different ways we can find average rate of change. So my example is from the Indianapolis 500. As you can imagine, the winning speeds for the Indy 500 has been increasing since the first year in 1911. You can view the data at the link I provided, Indianapolis 500 Historical Stats. I actually copied down the data here, but only the data from years 1911 to 2020. And what we're going to do is we're going to find the average rate of change given this data. Now, how can we find average rate of change? It totally depends upon the data that we're given. So number one is, what if we're just given two sets of coordinates? What is the average rate of change in winning speed from 1925, when the winning speed was 113.1 miles per hour, and 1988 when it was 144.8? Well, let's look. Here's my point. 1925, it's 113.1, and at 1988, it's 144.8. So I want to find the average change in the winning speed over time, 1988 minus 1925, and 144.8 minus 113.1 is 31.7 miles per hour. That's how much the winning speed increased. How many years did it take to do that? 1988 minus 1925 over 63 years. So 31.7 divided by 63, that's about a half of miles per hour per year. So every year, the winning speed increased about 0.5 miles per hour. All right, data given a table. What if we want to find the average rate of change from years 1920 to 1990? So here's 1920. Here is 1990. So if we're looking at a table, find the change in Y, or in our case, the change in winning speed, 1890 or 186 minus the winning speed of 1920 was only 88.6. Which honestly, I'm thinking that's pretty fast for 1920. I didn't know cars were able to go that fast. Of course, they were race cars. And so 186 minus 88.6 is 97.4. That was nearly 100 miles per hour faster. 1990 divided or minus 1920, that was over 70 years. So 97.4 divided by 70 is approximately 1.4 miles per hour per year. So if I use those two data points, the average change in the winning speed is about 1.5 miles for every year between 1920 and 1990. Now, what's another way to find rate of change? We can find rate of change, average rate of change, if we're given a graph. Find the average rate of change from 1940 to 2020. Well, in 1940, I can see from my graph the winning speed was about 120 miles per hour. And I can see in 2020, the winning speed looked to be, what is that? 160, about 160. When you're looking at a graph, think about it in terms of a line that connects those 2 points, and we're looking for the slope of that line. 160 minus 120 divided by 2020 minus 1940. So I've got a difference in 40 miles per hour over a course of 80 years. So now I'm back down to my 0.5 miles per hour per year, meaning the winning speed increased to 0.5 mile per hour every year. And now one other way to find the average rate of change is if I give you two inputs. So for an example, if I took all my data and I found a model for that data, an equation that described the graph, which I did on my calculator, and the model came out to be negative 0.0099x squared plus 39.843x minus 39,859. Use the equation to find the average rate of change between the years 1940 and 2010. So I'm going to plug in negative 0.0099. I'm going to plug in 1940. And you try it on your calculator too. And I get a winning speed of 177.78. Now I'm going to plug in 2010, so negative 0.0099, 2010, square it, add 39.843 times, what year was it again? 2010 minus 39,858. And I get 229.44. So according to our model, that's the winning speeds that should exist at 1940 and 2010 if we want to find the average rate of change in y's, divided by my change in x's, which is the change in time, will get us the average rate of change in that interval between 2010 and 1940. So 229.44 minus 177.78, 51.66. Over 70 years. 51.66 divided by 70, I get about 0.74 hundredths of a mile per hour change for every year. Now you might be wondering, why is it different? Shouldn't the average rate of change be the same? No, it would if your data was in a line, but if you have real live data, your average rate of change, I think you can see from your graph, totally depends on what years you pick. So if I pick these 2 years, this is my average rate of change. If I pick these 2 years, my average rate of change would go a different direction. If I pick these 2 years, here's my average rate of change. Your average rate of change totally depends on the data you use to calculate that average. And again, you can do it in 5 different ways. You can do it if you're given 2 coordinates. You can do it if you're given data on a table. You can do it if you're given a graph and you pick your points from the graph. And you can do it if you're given 2 inputs and a function and you calculate the outputs, the y values, before you calculate your average rate of change. So here's some notation that you will find when we look at average rate of change in calculus. Everyone's familiar with slope, change in y over change in x, your traditional slope equation. But sometimes instead of y's, we're going to see it as f of x's. We're going to see it often in that terms in calculus class. Now, let's take it a step further. You've done that before. You've done that in algebra. In calculus, we want to look at the instantaneous rate of change. So let's go back to our tennis ball. Find the average velocity for the following intervals. So I think we did 1, 2 up here. What was that average rate of change? Negative 48 feet per second. So go ahead and pause the video or try to do this faster than I am. And find the average rate of change between these other two intervals, between 1 and 1.5, and between 1 and 1.1. So I'm plugging in 1.5. So don't just watch me. Get out your calculators. And this is 64. And if I do f of 1, which is 84, and f of 1.1, negative 16. And this gets me 80.64. What happens to my average rate of change? Well, here it's 84 minus 64 over 1.5 minus 1. So it's 20 over 0.5, which is 40. And that's feet per second. 84 minus 80, 0.64 over 1.1 or 1, sorry, minus 1.1. And I think I did this backwards here, didn't I, up above? This should have been 1 minus 1.5. Which made it negative because we're going down toward Earth. So here I'm going to have 84 minus 80.64, 3.36 over negative 0.1. 3.36 divided by 0.1 is 33.6 feet per second. Notice what happens. My instantaneous rate of change is a little bit different, which makes complete sense. If I am finding the slope of these 2 points, and those points come a little bit closer, and even a little bit closer, the slope of those points are going to change. And what we want to do when we find the instantaneous rate of change is we want to find that change as the difference in my x coordinates, the difference in these points goes to 0. So let's go back up to our slope equation. I want to find the rate of change as x2 gets closer to x1. In other words, as their difference goes closer and closer to 0. But we write it a different way in calculus. And this is how we write it. We write it f x plus h minus f of x divided by h. What's h? So let's look on my curve right here. If I have my point here and my point here, this is x, and this point here is x plus h. H is just some value that I'm adding to x. I don't know why they pick h. I should research that. I have no idea why anybody picks h. And if I go up here, this point here is my f of x. And this point here, let's move this point over so I can go up. My f of x plus h, let's make this right here. This y point right here is f of x plus h. So when I want to find slope, I find change in my y's, which is f of x plus h, divided by change in my x's, which is x plus h minus x, but the x's cancel out, and we're left with just x. This is just the equation of slope. And we want to find this equation as this x value, as these 2 points get closer and closer to 0, as the h value gets closer and closer to 0. And that's our limit. The limit as h goes closer and closer to 0. Now, how do we do that? How do we find the instantaneous rate of change of a function with the given value? We simply have to plug it into this equation. And it can get kind of messy. We'll show you a shortcut later, but not this section. So I want to find f of x plus h minus f of x all over h. So what we do is we plug in x plus h into my function. So negative 16 x squared plus 100. We want to subtract that function, negative 16 x squared plus 100. And we're going to divide that all by h. Now, with quadratics, it's kind of ugly because we have this expansion. It's not too bad. X squared plus 2xh plus h squared plus 100 plus 16x squared minus 100. The hundreds cancel. I have to distribute my 16, negative 16x squared minus 32, that's 16 times 2, x times h, minus 16 h squared plus 16x squared. And remember, we're still taking this whole thing and we're dividing it by h. So I'm still taking this whole thing and I'm dividing it by h. My 16x squareds will cancel. I can cancel one of the h's, and I'm left with negative 32x minus 16h. Well, what's my instantaneous rate of change? At x equals 1, it's negative 32 times 1 minus 16, whatever my second point is at, 16h. So negative 32 minus 16, h, what is my h at? Let's add the limit as h goes to 0 because we want the instantaneous rate of change. And I get negative 32. So at 1 second, right here, 1 second, so this is 1 on my diagram, the slope of the line tangent to that curve would be negative 32. That's my rate of change. I found this function right here. I found that function. That was my negative 32 times 1 minus 16h, and I want to evaluate that function as my h goes to 0. Let's try another one. Let's try a linear one. I want to find the instantaneous rate of change of y equals 6x plus 2 at x equals 15. So I want the limit as h goes to 0 of f of x plus h minus f of x divided by h. So I want my limit as h goes to 0. F of x plus h is 6x plus h plus 2. I simply plug x plus h into the x in my function. I'm subtracting my function. Those are my y's. And I divide it by h. So my limit as h goes to 0 of 6x plus 6h plus 2 minus 6x minus 2 all over h. The 2's cancel, negative 6x cancels, the h cancels. The limit as h goes to 0 of 6 is simply 6. Which makes total sense. You have a linear function. What is the slope of a linear function? What is the slope of this equation? It's 6 at every point. At every point, my instantaneous rate of change would be 6. So for a linear function, it works. We don't have to do all this work because we know the instantaneous rate of change is always 6. For a parabola, the instantaneous rate of change changes. It changes depending on time. So if we were looking at the instantaneous rate of change for the second 2, it would be negative 32. I would put in 2 seconds, which would be negative 64. So I would look up here at 2 seconds. If I drew the line tangent to the curve there, this slope would be 64. This slope here is 32. They're both negative, 32. So for quadratic functions, your instantaneous rate of change changes depending on your x value. For linear, it doesn't. It stays the same. So here for my quadratic, my rate of change is negative 32x. It depends on my x value. Let's do one more. We'll add a page. So this is one right here. What is the instantaneous rate of change of y equals 2x squared plus 5x minus 1 at x equals negative 2? Well, let's go ahead and look at the limit as the change in x's goes to 0. I'm going to plug in my x plus h. So I have 2x plus h squared plus 5x plus h minus 1. Think of that as just your first y value. Here's my second y value, where my point has an x coordinate of x, and it's all over h. Now we have to expand this. So I have 2x squared plus 4xh plus 2h squared plus 5x plus 5h minus 1 minus 2x squared minus 5x plus 1. That was a lot. I distributed my negative. I expanded this to x squared plus 2xh plus h squared, and then I multiplied it by 2, all in one step. Now I cancel, and usually when you do these different quotients, a lot of things cancel. A lot of things cancel. Then I cancel the 1, and I am left with 4xh plus 2h squared plus 5h, and I'm looking for the limit of that as h goes to 0, all divided by h. Cancel the h's that cancel, and I have 4x plus 2h plus 5. What's the limit as h goes to 0? 4x plus 5. I have an equation for the instantaneous rate of change. So when x equals -2, the rate of change is 4 times -2 plus 5, which is -3. And that rate of change would be completely different if my x value was, say, something like 7. Then my rate of change would be 4 times 7 plus 5, which is what? 28, 29, 30, 1 through 2, 33, which would be 33. Which makes complete sense because this is a parabola, 2x squared plus 5x. It's a parabola. The rate of change is going to be completely dependent on what points you pick. Just like our Indy 500, if I pick these 2 points, my rate of change is that slope. If I pick these 2 points, my rate of change is this slope. And if I pick these 2 points, this is my rate of change. Instantaneous rate of change talks about a tangent line, the slope of a tangent line. So the slope at this tangent line is this value. At this tangent line, it's this value. At this tangent line, it's this value. We're looking at the rate of change, or the slope of the tangent line, when x is at -2. And then we're looking at it when x is 7. And our equation for the slope of that tangent line is 4x plus 5.